Welcome to another virtual SDC2020 presentation. My name is Ryan McKenzie. I am a senior performance engineer at iXsystems. iXsystems is a company that has a software and hardware portfolio that is focused on storage and in particular ZFS based storage solutions, from free at-home software you can run on your own hardware all the way up to enterprise software with HA features and full support that you can run on the hardware that you buy from us. So what I typically do when I'm giving a presentation in person is I like to take a little poll. We are going to be on Slack. Even though this is pre-recorded, I will be monitoring Slack. So just go on the Slack channel here right now and shout out if you have any experience with ZFS, if you work for Oracle, or if you play with it at home, if you have a FreeNAS, soon to be TrueNAS Core system at home, or if you are using TrueNAS iXsystems products at work. So just give us a little shout out there in Slack. I'll go ahead and get started with my presentation. Today we are talking about a case study. Now, last year my presentation was a more hard, getting into the guts of how L2ARC works and how L2ARC benefits us in the era of having large NVMe devices, using them as L2ARC. This is sort of more of a use case study of, okay, now in a measurement environment, you're measuring the performance of a ZFS storage server. How can you make sure that the measurement period during your benchmark is going to be steady? So the problem statement is where we'll start. What are the challenges associated with monitoring for steady state in an array-wide environment? What are the previous work that has been done to solve a piece of this or most of this? My proposed solution and how I implemented it, and sort of some observations. There's going to be a lot of slides in here I'm going to skip through during the video presentation that will be able to be downloaded in handouts that are going to be more for your reference. So what is a performance engineer? What is a performance engineer looking for in their data? Performance engineers like me want their data to be repeatable. So in other words, I want to be able to launch a benchmark on a system and have that benchmark go out and get me a test result. And then, I don't know, 6 months later, I want to configure that same system the same way and run the same benchmark and get the same or very, very similar results within a margin of error. So that's a good thing, repeatable test results. And also that we don't want them to vary on test order. And what do I mean by that? Well, let's say my normal way of doing things is I run 100% reads, and then I run 100% writes, and then I run my mixes of reads and writes. Well, let's say we fix a bug that has to do with reads, and then a few months later I go back and I want to retest the reads. Well, are the reads going to be better if they are tested by themselves or if they're tested after doing the writes? So we want each individual workload to be repeatable no matter what order it is run in the sequence. We also want the test results to be applicable. So we want them to be an accurate reflection of how the system should perform under the given load. We don't want to have our benchmark be so synthetic. We don't want to induce such a synthetic state in the system that it really doesn't mean anything to our potential customers or our existing customers, or, put totally fake things up on the spec sheets. So the problem with this is storage systems are pretty complex. I mean, most of the people here at SDC know that even testing a single SSD device is kind of dicey to get that repeatable and applicable results. So testing an entire stack of, you've got your single device, and then you've got your RAID, and then you've got your, whatever protocol is you're presenting that RAID device to. Is it iXsystems? Is it going to be some file system? Is then what's on top of that file system? Is it NFS? Is it SMB? Is it some sort of application resident on the array? It's super complicated. There's lots of layers, and test time is very limited compared to customer time. Now, when I tell my my managers and directors that a certain feature is going to take, a month or a quarter to test, they think, oh my gosh, that's a lot of time, But in reality, we're going to have some systems out there that are going to be running this situation, and they're going to. We've seen systems with over a year of uptime going on these things, and probably more. I'm not really in support. I'd say we have some more longer uptimes than that. So even though it does take a long time to thoroughly test a new feature or to thoroughly test how our system is going to respond in a particular configuration to a particular workload, that is nothing compared to what the customers out there in the real world are going to see and the users at home are going to see. So we got two goals, or I have two goals in my testing. Steady state detection is what I'm going to be addressing today. Basically, what that's going to do is it's going to prevent measuring the performance of the system in a volatile state. We don't want to measure the performance if it has a artificially high level of performance or if it's at an artificially low level of performance. We want the system to be non-volatile at the time of measurement. Preconditioning is sort of an ongoing hobby of mine right now. We want to induce this steady state. So now that we can detect the steady state, I'm trying to induce the steady state as quickly as possible. But again, without making it super, without making the system, especially with ZFS, is kind of self-tuning. And so if you were to go off and run something that's specifically designed to load the ARC and load the L2 ARC as fast as possible, and then come off and run this customer workload like a VDI workload, the system's not even going to be in the proper state. So my current rudimentary approach is just to, whatever workload I want to measure, I just run that workload at the highest thread count or at the highest requested load that I want to run, and I run that until steady state is detected, and then I do my measurement. Sometimes it takes a long time, so that's some sort of future work that I have. Previous work, well, as we discussed, the array level detection can be viewed as multiple layers, and multiple layers on top of. I need to make a note of that on slide 5, and I'll correct that for the handouts. On top of. So you got multiple layers on top of your single device steady state detection. So SNIA has a widely accepted and applied solution for that problem. So we're going to look at that right now. Here it is from the solid state storage performance test specification, version 2.01. Steady state is device's steady state when for the dependent variable, which is typically in your SSD testing, it's typically IOPS or bandwidth or latency is what your Y value that you're tracking. We're basically looking at what the range is. So essentially we're creating a box. We're essentially saying over this measurement period, and that's the width of my box, there's this measurement period, I can't have any data points that go outside the box, right? So that's one box. And then another box you're creating is, now I've got this smaller box, and the slope of the linear curve of all of the values measured in that time period can't be higher or lower than 10%. So again, visually this is what it looks like, and Mr. Easen has done a good job of putting this out there in multiple places. I actually chose it from the this 2011 presentation, you can actually see that the rectangle, the box that we're creating, the measurement period left to right, and then the 20% data point exclusion or excursion is the big yellow box. And if you have any data point go outside of that, then no matter what the slope is, if you have a data point outside of that, then you're not steady. And then, you know, you have your slope measurement of your linear best fit, and it has to be inside the smaller green box there. So that's what we're going to use, but what are we going to apply it to? We're going to select multiple metrics on a ZFS storage server that we can gather while the system's under load with relatively low impact to the system or no impact. And each metric is going to be subjected to that determination. So each individual metric we pick out at each time step, we're going to say, is this steady? Is this steady? Is this steady? And I've got 10 metrics that I have defined here. So ARC metrics, there's 4 metrics of ARC. ARC is very important in a ZFS file system. ARC is sort of self-tuning, it can actually tell you a lot about the state of your system if some of these things are steady or if they're wildly changing. The ARC size, of course, is going to let you know how much of the ARC is being used at the current time. Most recently used, most frequently used, that's what MRU, MFU is. So if you have a lot of most recently used data in your ARC, then you're not having a lot of, you're going to either be having a lot of writes. Every write that comes into ARC creates a new block in ARC. So if you got a write heavy workload, you're going to have a lot of MRU. If you have a very metadata heavy workload, or if you have a very small active data set that fits inside your ARC, you're going to be hitting those blocks over and over again, and you're going to have a most frequently used. So, and the balance between those two things is very important. Also, data and metadata. So this is not data and metadata in terms of your client workload. This is data and metadata of ZFS. This is your volume block metadata, your ZFS metadata. And by the way, this testing is not with fusion pools. Fusion pools would complicate things greatly because then you would have special pool devices where your metadata, your ZFS metadata would go. ARC hit ratio is one that we look at. L2 ARC metrics only if applicable. So if the system is loaded with an L2 ARC, we will gather these 3 metrics: L2 ARC size, L2 ARC write rate, that's basically how many blocks or bytes we are writing to the L2 ARC over the intervals, and our hit ratio. So how much good is the L2 ARC doing us, essentially. ZFS metrics, we're going to pull the IOPS and the bandwidth from operations per second and bandwidth from the pool that we reside on, and also the average op latency of the pool, or the total response time of the pool would be a more accurate way to put that. Something that I sort of did in my implementation, this is not part of the theory of it, this is implementation. I decided that all metrics must do no harm if the collection fails. Because, you know, sometimes we have moving targets in the real world. You have a sysctl variable that's there in one version of the code, and then the next version of the code, the sysctl is gone. Or maybe you have a tool like IOStat that the syntax of it changes, and so your parsing of it fails. So really, we've got some things in here that some of these metrics collections can fail. And so what we don't want to happen is we don't want to have the system basically run indefinitely because we are failing to read some of these metrics. So what I've chosen to do is, if we fail to parse or gather any of the metrics, then that metric is just pinned as steady. All the non-performance metrics are normalized to a percentage. So basically, Something like arc size would be expressed as a number from 0 to 1, where it's, you know, essentially how many blocks are in the arc versus how many max blocks the current system will allow. And that just helps with charting, and it helps with math. It helps with normalizing everything to go ahead and put everything down to percentages. Now, of course, we don't know a priori how many IOPS the pool is going to do. We don't know a priori how much bandwidth the pool is going to do. So we can't really normalize that to a percentage. So those are just raw numbers. All right, so here's some implementation, and a very important note in my implementation. In this test environment, we have the luxury of knowing which pools the active data set resides on, how big the active data set size is, and we know, essentially we know that the caches have been cleared before the first test. So essentially we know that, okay, I rebooted the system and cleared the ARC and the L2 ARC, and so now I started this test sequence, and so everything in the caches is part of this active data set. Now, in the real world, you're not going to have these luxuries, which is why this methodology really is only going to work in test environments. So here are some implementation details on how each of these metrics are implemented. I'm probably not going to go through all of these in a lot of detail. This is mainly for your reference. So if you want to go and try to do the same thing I've done here in your test environment, this is sort of a checkup on me. If you're reading these slides and the handouts later and you go, oh wow, there's a better way to do that, there's a more accurate way to pull that stat, please let me know. So here's currently how I'm implementing these. So essentially the arc size is pulled from a K-stat syscontrol of what the current size is, and that's the uncompressed size, and then what the max size is. So it's essentially just a percentage. The MRU MFU makeup is basically if you are at 1, you are all most recently used. So if you're at 1, you're really scanning your arc real bad. You're doing a lot of writes, or you're not getting a lot of rehits on things. And if you're down at 0, your arc is getting a lot of rehits on blocks. So it's really skewed toward most frequently used. So that shows the skew between most recently and most frequent use. The data metadata makeup, again, this is going to be if the number is 1, you're going to have a lot of data in your arc, and if it's 0, you're going to have a lot of metadata in your arc. That's just the way I did the math. Because mainly I'm not looking to report these numbers necessarily. I'm looking to make sure that this is not fluctuating wildly. I'm trying to make sure that we're not bouncing back and forth from data to metadata wildly. I want the arc to be sort of settled. And then of course the hit ratio. Okay. L2 arc size is essentially calculated the same. Only what I've done is gotten the capacities of the cache devices from zpool status. Now the write rate is pretty interesting, because the write rate you have to know, you have to keep track of how much was written, because it's a cumulative stat in the system. It's a cumulative stat, so the L2 write bytes is cumulative, so I have to look at it in 2 intervals and get the difference. That's how many bytes were written. Also note that this value can be greater than 100%, because the L2 arc write max can actually be boosted under certain circumstances. So right after a system reboot, for example, when the L2 arc is empty, we're going to write to the L2 arc very aggressively if you want to look back at my talk from last year's SDC 2019 to see how the gory details of the L2 arc works, that would be a good reference, I believe. And then again, the total number of the number of hits divided by the total number of requests coming through the L2 arc is how we do hit ratios. And that's actually based on the arcs, the way it's done in ArcStats PL, which is a tool that goes way back in ZFS communities. Here's an interesting note on zpool IOstat. Zpool IOstat is where I get the ops and the bandwidth from. The first line, if you just do zpool IOstat with no parameters, it's just going to give you the cumulative stats for all the pools on your system, which is not very helpful. So what I do is I collect 2 intervals, and then I look at the last interval, and that's going to be a difference. That's going to be the second line will always be what was done the last interval, as opposed to a cumulative stat. So you get ops bandwidth, and you get your latency. So that's what the output looks like, and it's pretty easy to parse. Although I'm going to note that I have a problem right now with parsing because of the little dash there in the wait times. So a lot of the charts you're going to see today are not going to be considering the zpool latency in their steady state calculation, because I had trouble parsing that, because I think that's a new thing, as opposed to reporting 0 and now reports a dash. All right, so here's the engine, and we're going to get into the meat of this here. I did a Python thread class instance, so when you instantiate the thread, it actually goes off to the system and preloads all the constants from the system, like the L2 arc capacity, the arc max. It does all that once before it even starts running. Now, when you start the thread, it actually spends a certain amount of time loading the window. So we're talking about this box. We're creating this box. How much time your window is how wide the box is. So we're going to spend a certain amount of time loading metrics every so often, and we're going to build this box. So what we're actually doing is we're building a short history of data for all these metrics. Now, if steady state is declared, what happens is essentially my runtime automation for my benchmark spawns this thread, and depending on the benchmark, if it's VD bench, you can use a monitor file. If it's SFS, you can use a monitor script. So the benchmark has module, or the steady state thread has modules to be able to signal the benchmark. So the benchmark starts and begins its precondition warm up, and then it just sits there and does warm up forever until my steady state thread comes back and signals it in whatever way is appropriate for the benchmark and says, okay, you can go now, you can measure. You can stop this early, so you can Control C it, or if you reach you can't let the system run indefinitely if it's not going to reach steady state. So there's actually an absolute timer in there. I think it's defaulted to 24 hours, but if the system's running that long and hasn't reached a steady state, usually you can just, terminate the experiment, because something's wrong, or you're not going to get there. So we collect all the metrics, every interval. The default interval is 15 seconds. Once a window of intervals, that's the window is the width of our box, is collected, we're going to start calculating the range and slope of the data points within that window. So we default to 20 intervals. 20 intervals at 15 seconds is 5 minutes. Yes, 5 minutes. So we recommend that the window size be at least as long as our benchmark measurement period, and 5 minutes is a pretty typical measurement period for a benchmark. So here's what we got. So the solution I'm testing is a FreeBSD OpenZFS based storage server with 512 gigs of main memory. It's got 4 1.6 terabyte NVMe drives, and these are big enterprise grade dual port SAS PCIe Gen 3. You know, these are not, you know, M.2 NVMe drives that you boot off of. These are big players. There's 142 2 terabyte SAS HDDs in 71 mirrored VDEVs. We have 100 gig NIC, optical QSFP plus. Tested it with a lot of different protocols, a lot of different situations. iSCSI, NFS, SMB. We're going to focus on NFS v3. Number one, NFS v3 is more interesting in terms of you get more metadata, file system metadata, as well as client metadata activity going on, and you also have a lot of sync. So you're exercising more data paths with NFS, so it's a more interesting thing to look at. But also, it's just for completeness. Some of the other tests did not, for whatever reason, they didn't log the steady state metrics. So NFS v3 was the most interesting and the most complete, so that's what we're going to look at. Now here is what I will be showing. Let's see if I can get my laser pointer. Okay, laser pointer. So the lines up here, these ones that don't have points on them, are the calculated value of the metric, and you can see that those are on the left axis. We go from 0 to 1 because they are all normalized to a percentage on most of them, and then we have the different categories. So this chart is our arc, this chart is our L2 arc, this is our ops and bandwidth for our pool, and this is our latency for our pool. Now, the corresponding colored dotted line represents whether or not we've determined this to be steady. And you can see that essentially, even though they overlay each other, you can see that these are our 20 intervals for our window. So we're loading our window, we're loading our window, we're loading our window. And the window of data looks like this, looks pretty steady. So you can see that as soon as the window is over, the very first time interval after the window, all the metrics jump up and say, yes, I'm steady here on the arc. And you can kind of visually see that too. And by the way, that's the way before we implemented this, that was the way we would determine it. We would run for a certain amount of time and look at the data and go, oh yeah, that looks steady, you know. So this is much better. L2 arc window, you can see that the L2 arc writes per interval are pretty bursty, and that's across the board. I don't think any of the data I'm going to show is going to show that metric ever being declared steady. So that's an interesting one. You can see that the L2 arc size is very tiny because we have a very tiny active data set size, and we're doing almost all writes. So we're not actually loading anything into the L2 arc, so we have nothing going into the L2 arc, essentially. The system gets really steady really quickly with data set sizes that fit in memory. So, you know, that's kind of the rule of thumb. So again, I want to note that during all of these tests, something was wrong with ZFS parsing. So the latency you're going to see is the latency line is always zeros, and so we're always going to call that steady. So that didn't really hold us up. It's again something I need to fix. I need to update the parsing for that. So look at the read versus the write, and you see some very interesting things. So let's focus on arc. On the reads, you can see that we are actually down here about 40% into the most frequently used. So we're getting a lot of rehits, and that's good. That's what reads are doing for us. So we're getting a lot of rehits. But over here, we're getting almost all, actually, we are getting basically all new blocks written to ARC because it's all right. So synthetic, all 100% right. So it's neat to see. It's neat to see that there's data here that's actually confirming how you believe in your mind the system works. Like, you know, sometimes you just have to take a step back and go, yeah, this thing's actually working the way I expect it to work. That's pretty cool. So the arc size, of course, is above 80% in both cases. It's a little bit larger for writes, and that's because we are going to be more aggressively using up ARC blocks when we have a write heavy workload, because every single write, if you go back to my presentation last year on how ARC and L2 ARC work, every single write has to have a block available for it in ARC. Otherwise, we stall writes and the write response time goes way up. We don't want that. So pretty neat stuff here. You can actually see the performance difference in 20 megs per second reading from ZFS. Now, that's because a lot of these requests are just being serviced by ARC here. The pool is not doing a lot of work with 100% read cache hit workload. It just isn't. The pool is not being engaged very much whereas on the writes, and this is NFS writes, the pool is doing a lot of work. The pool is doing 800 megs per second because NFS is a sync heavy protocol. So, and we're doing all writes. So it's pretty neat. It just sort of validates that everything's working the way we expect it to work. This is a more interesting graph. This is a 4.8 terabyte. You can actually see that the steady state detection runs for a very, 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 very long time on this, and I'll show you why. But you can see that, you know, essentially the dotted lines are now all just blurred together. It's pretty interesting to see that the ARC is very steady on reads with this very large active data set size. You can see that, you know, we're doing ARC misses and we're having to do a demand page. We're demand paging things into ARC, and so you got this fluctuating ARC size, but it's within a steady band, which is good. We have this fluctuating data metadata, which is within a steady band. Now, the most recently and most frequently used is almost all the way down at most frequent. So we're doing a lot of rehits because, you know, this is a very huge active data set size. A lot of it's out there on disk, but we're also rehitting a lot of metadata blocks. So over a long period of time, we're getting the client level metadata into ARC, as well as the ZFS metadata into ARC. So we're reheating it a lot, but that metric doesn't get steady. In fact, none of the metrics other than the hit rate get steady here, which is interesting. They don't get marked as steady. Also, we have L2 ARC, you can see, is very gradually warming up. Now, this is kind of a problem, and we'll talk about this a little bit later, is that the L2 ARC is warming. The slow warming of L2 ARC over a very long period of time is not enough to trigger our steady state to say, no, don't measure yet. But really, we shouldn't measure yet. So there's a heuristic that I've added that kind of waits until the L2 ARC is warm. So you can also see over here on very, very large on writes, we get to a steady state. Actually, we get to a steady state pretty quickly, but that's you know, that's because we're not, that's because we're riding, and riding does tend to be, at least in the terms of arc, it tends to get us steady more quickly. Now, these are fluctuating, but notice we haven't run for nearly as long here. So this fluctuation up and down in these metrics is probably about the same as this in terms of magnitude. The L2 arc riding per interval is crazy bursty. Again, it never reaches steady state. And you can see that more and more and more IOPS and bandwidth are being serviced by the pool. And that's because the pool is starting to rely more and more on L2 arc as the L2 arc gets warmed. So this is a mid-size ADS with a mix. So we're going to go, this is kind of a more realistic situation. We have a 70-30 read-write mix. We have 1.2 terabytes of active data set size. And you can see that as we continue to run over time, we're going from most recently used down to most frequently used as we start loading, you know, rehitting blocks. Again, we have this slow march of the L2 arc size going up. We have the very bursty writes per interval of the L2 arc. And steady state metrics are mostly satisfied early on, but the L2 arc warm heuristic is met much, much later. So what's happening here is we're waiting for 1.2 terabytes of active data set size, or a certain percentage of that, to get into arc plus L2 arc. So, you know, arc gets up to around 80% real quick, and then L2 arc, you know, it's warming, and then at some point it reaches this threshold and says, okay, well, the active data set 1.2 terabytes is in there. So note that we have a really huge L2 arc. So even at less than 20%, we're probably talking, let's see, we got 5 terabytes in there. So, you know, we've got close to a terabyte in L2 arc just offhand, and then we've got, you know, 450 or so gigs in arc, and that's where we meet our threshold. We're warm, right? So we declare steady state. Sequential, I will say, sequential is not very exciting. ZFS does a very good job with its prefetcher of detecting a sequential workload and you know, being very steady. So I'll just skip through these pretty quickly because they, again, are not very exciting. You can see all of our metrics are fairly steady, especially with this small active data set size. Here's large active data set size, much of the same. Really, the only thing that is holding us up here with these reads is, let's see, there's got to be some heuristic that's holding us up, because you can see that all of our metrics are steady for a long period of time. So there's one of my heuristics is saying wait. So otherwise on writes, you know, we immediately get steady. So here's our 50-50 mix with 1 meg sequential with a 1.2 terabyte active data set size. This is kind of the sweet spot. It's the more realistic read-write mix. It's the more realistic active data set size, and you can see that it is fairly stable, with the exception of the IOPS coming from the pool. Now, the reason that the IOPS coming from the pool is fluctuating so wildly is that sometimes we're hitting L2 arc and we're getting a lot of IOPS and we're getting very low latency, and sometimes we're having to go all the way out to hard drive, and that is that's what's causing the burstiness there. Overall, in terms of bandwidth, it's not really affecting us very much. in the absence of L2 arc, so we don't have any L2 arc here. When I run sequential tests, I don't put L2 arc in the mix. So the overall number of metrics and the number of metrics needed to pass steady state are reduced by 3. So we've got 3 L2 arc metrics here. If my engine detects that there is no L2 arc installed in the pool, using again zpool status, then we will actually say, okay, there's no longer 10 metrics we're trying to satisfy. There's 7 total metrics. And then if I'm a little bit forgiving and I say, well, I need 7 of 10 to be considered steady before I go on, I now have to do 4 of 7, right? So again, this is all geared toward not being perfect, but helping us get steady state in most cases, and not letting the system just run indefinitely, because we don't have that kind of time. Go back to the first or second slide there. We don't really have the time to wait indefinitely on a system. So some challenges we ran into when I started looking at this data: workload matters. Large block sequential workloads have seemed very stable, especially when you run them with no L2 arc. You know, of course, you saw in my talk last year, we do run them sometimes with L2 arc, specifically when we have a fast enough L2 arc for it to make a difference. But it's definitely more stable and warms up quicker without L2 arc. If you look back to my talk I gave last year, actually the writes that are being written from ARC into L2 ARC actually take system resources away from client visible writes. So, which is fine if your L2 ARC is going to give you a great benefit. So what you can do is you can put up with a little bit of fluctuation in the write performance of your system for a certain amount of time. Then you get this fully loaded L2 ARC that's really helping your performance. But in the shortened, abbreviated amount of time we have to do feature testing, sometimes we just leave it out. Writes are somewhat unstable for random workloads. We did notice that bursts are correlating to L2 ARC writes. So again, that is the thing I was talking about earlier, where if you're taking blocks and writing them into the L2 ARC devices, that's actually using up some of the system resources that you would be using on your client visible writes. Small active data set, especially if it fits in ARC, is very stable. The I/O path is almost deterministic in that case. Large active data set size always takes longer to reach steady state, but it's only significantly longer if there's an L2 ARC because of my heuristic to do L2 ARC in the pool. Some metrics may never reach steady state, and we saw that with the L2 ARC writes per interval. The L2 ARC writes per interval is very bursty. And in fact, I may remove that for future versions of my steady state detection, because if there's an L2 ARC in the system, you can just about guarantee that the writes going to it are going to be bursty. Long and slow warming of L2 ARC is an issue, and this is a very large active data set size, 4.8 terabytes. It's a 32K random mix, 70-30 mix, and you can see this is what I'm talking about. Look at the lower left. The pool is gradually increasing in performance, but it's not increasing extremely enough in order to say this is not steady. So had I measured my system performance somewhere in here, I'd be leaving performance on the table. So what I really want to do is I really want to measure the performance somewhere in here. You can actually see that the most frequently used is probably one of our more important metrics actually for steady state. When it actually becomes stable, but again, it hasn't violated the SNIA definition of stable, because look at all the Booleans, right? It actually is over here in this range somewhere, which again you can see is where we've reached peak performance. And that's all because of L2 ARC. We're getting more L2 ARC headers in the ARC, and you can actually see that the L2 ARC size reaches a peak about that same time. So what I'm trying to do with my heuristics, you can see that the SNIA steady state metrics are good. up to a point. But when it comes to an L2 arc, they're not as good because the L2 arc is a long, slow process. So what I'm trying to do in my heuristics is find this sweet spot here, which is also here, which is also here. That did a pretty good job. I was pretty proud of that. So here's our optimizations I was talking about. We don't have to satisfy all the metrics, because if we wanted to satisfy all the metrics, some of them would never be satisfied. This is tunable, by the way. I use 7 of 10 because I'm an 80-20 kind of guy. Maybe a 70-30 kind of guy. I've got a limited amount of time to test these systems, and so I want my results to be good. I want my results to be repeatable. I want my results to be applicable, but they don't have to be perfect. There is a margin of error I'm willing to accept in order to save, a lot of time. But you can tune that also. If the metrics are satisfied, we still wait until 85% of the active data set size is in cache. And again, this is something that I have the luxury of measuring because I know where all my data is. I know how much data I'm using. I know that the system was clean before I started running, so only my data is in cache. But in any test environment, you would have the ability to set that up. So we wait till 85% of the active data set size is in cache. Although if our caches are getting very close to being full, so in the case of like a 4.8 terabyte active data set size on a smaller storage array that maybe only has a 600 gig SSD for L2 arc, the arc and the L2 arc are getting both kind of full. Active data set size is not all in there, but we don't have any more rooms, much more room. So we're gonna put a threshold there also. Okay, results, overall results. Well, test engineer time was reduced by 1/3. So really my first test sequence, my first product cycle essentially at iXsystems, I spent a lot of time, especially on the larger systems with a lot of L2 arc, manually deciding whether or not the system was steady, whether or not that was a good repeatable result, especially with the large L2 arc. So, and a lot of times that would take 3 or 4 iterations to get right. So from the first test development cycle to the second test development cycle, I reduced my personal hands-on time with the systems by about 30%, which is cool. System utilization has more than doubled to the unattended time. So what I would do very early on was the first test cycle was I would run the system for 6 hours, then I would check, or I would run it for 12 hours, then I would check. Sometimes that 12 hours ends like at 7 p.m. after I just got home, and I'm not going to log back in and start the test overnight, so the system doesn't run overnight. These systems are, especially these big high-end systems, are kind of hot commodities in our lab. So we wanted the utilization to go up. So now these tests can run unattended 18 to 20 hours per day when I have my hands on them. So very good result there. That's something you can take to your performance test leads. We do have better repeatability. So the anomalous measurements that I was seeing when I was manually determining things, and maybe I would run out of time and I would just say, okay, this is good enough. And then a few months later, we would run it and find out, well, no, that wasn't good enough. I should have ran longer. All that's pretty much been eliminated. We now have this has been in use for 2 complete product cycles. So now we have comparable baselines, so we can do things like regression analysis, but there's still room for improvement. What I will be improving is a better way to collect the pool op latency and fixing that parsing. I'm going to remove the L2 arc writes per interval metric because it's never steady. I would like to add metrics for the different classes of device. This is mainly for fusion pools coming up. So we have data VDEVs, we have log VDEVs, we have cache VDEVs, we have special VDEVs for fusion pools for metadata. what I'd like to do is get the device busy average for all those different classes, maybe some other performance metrics for the different classes. You know, instead of just saying, here's the IOPS that my pool is servicing, here's the latency of my pool, all that stuff. Why don't we look at those metrics for all the data VDEVs are doing this, and the log VDEVs are doing this, and the cache VDEVs are doing this. So thank you for your time. I will, of course, this is pre-recorded, but I will be on the Slack taking questions. So hit me up on Slack. What I want to do, though, is show these references. When you download the handout, these are the references where you can pretty much get all of the information on how ARC works, how L2 ARC works, how the SNIA solid state storage performance test specification says to implement steady state. Basically everything you need to reproduce this this test. So, and don't forget to rate the session. So at this time I'm going to end the recording, and I will, looks like, take about 10 minutes of 5 to 10 minutes of questions in Slack. So again, thank you for your time. It's a little different this year than it has been in years past, but I always appreciate participation in my sessions. Thank you.